Lab 4 Refrigeration, presented by Brittany, Elizabeth, Anna, and Christine. To give some background, Machine Chillers Inc. developed a cooling system based on a vortex tube using air as a working fluid. We have been tasked with modeling the system and determining its capabilities. We want to cool a device using mechanical work and characterize first the compressor's ability to pressurize the system, second the vortex tube's input and output properties, and third the heat and energy transfer at the load. And pictured here in Figure 1 is the vortex tube component and schematic. The equipment used in this experiment includes the experiment setup, which involves the pressure regulator, the heat exchanger, the accumulator, the vortex tube, the aluminum load, the pressure, flow, and temperature sensors, as well as the LabVIEW and the MyRio. For week 1, we want to characterize steady-state behavior of the vortex tube and the motor and compressor by collecting and plotting data at various pressures. We then use that data to find out how much energy is being supplied and removed by the heat exchanger and the accumulation tank. We then use that data to determine thermal resistance and compare to the theoretical thermal resistance. Shown here in Figure 2 is the experiment set up for the first part of week 1, which uses shop air.
First, we characterize the steady-state data from the vortex tube. In Figure 3, the temperature versus time for 0 psi is shown for the outputs at the load, T4 cold, T4 hot, and T5. Because no air is being put through the system, all the values should roughly be at ambient temperature. But as shown, there is some slight variation from the sensors. The average offset from the ambient temperature was determined for each sensor and then accounted for in the rest of the trials. The system response for the 20 psi input from the line air is shown in Figure 4, and the steady-state segment is highlighted where the output temperatures level off. There is some noise which occurs during the steady state, but through averaging and accounting for the sensor offset, there can be a high level of confidence in these values. The trends are also as expected when compared to the initial ambient temperature. Figures 5, 6, and 7 show the steady-state data for 40, 60, and 80 psi from the line air. Again, there is some continued noise, but the values remain constant overall. As the pressure increases, the cold air exiting the vortex tube gradually becomes colder, and the hot air exiting the vortex tube becomes warmer. This results in a greater cooling effect on the load. This observation is solidified when comparing the average steady-state temperature to the absolute pressure. As the pressure increases, the temperature of the cold output decreases, as shown in Figure 8, and the temperature of the warm output increases, as shown in Figure 9. Note that for the cold temperature, some inconsistencies were found in the data trends as represented by the remote data, perhaps due to different operating conditions on the days these were taken. For the mass flow rate versus absolute input pressure plots shown in Figure 10 and 11, as input pressure increases, so does the mass flow rate of both the cold and hot flow, as essentially the volume flow rate of the entire system is increasing. Again, some discrepancies in data trends occur between the remote data and the lab data.
After determining how the vortex tube functions through initial experimentation, characterizing the function of the system with motor compression was then explored by switching the experimental setup where the air would flow from the motorized system instead of pressure from the MRDC building that was used before. Figure 12 shows what the ambient steady-state condition of temperature versus time would look like at 0 psi. As can be seen, there is a lot of noise in the signal. Figure 13 shows what the temperature versus time graph looks like for the refrigeration system at 20 psi. It's important to note that T3 is assumed to theoretically be the same value as the ambient temperature due to properties of the system, and Figure 13 shows that this assumption may later be a source of error on the graph, and how the motorized system effectively cools the system from 342 Kelvin to 315 Kelvin. Similarly, 40 psi and 60 psi pressures were implemented to the system, as Figure 14 and 16 show. With the higher pressure, there seems to be an increase in the temperature of the system over time, generally speaking. Additionally, Figure 17 shows the positive linear correlation between the motor speed, measured in revolutions per minute, and pressure of the system, measured in pascals. This correlation was calculated to have pressure of the system equal to 91.142 times the revolutions per minute plus 42,599.637 as the pressure offset. This shows that the higher motor speed and pressure will cause an increase in the temperature of the system, as was seen in previous results when the pressure increased on other slides.
This slide shows the relationship between the heat transfer rate and the air pressure as the air travels through the heat exchanger and accumulator. The heat transfer rate is calculated using equation 1, utilizing T1, T3, specific heat of air, and the mass flow rate of air. This plot only contains two data points, 20 psi and 60 psi, because the mass flow rate of air was not collected during the experiment, and the online data only had the flow rate for those two pressure values. More mass flow rate data for air pressures between 20 and 60 would help determine the relationship between the heat transfer rate and pressure through the heat exchanger and accumulator. Going back to the steady state analysis of the refrigerated load, the insulation thermal resistance, RNs, can be measured experimentally and calculated theoretically. The experimental calculations are shown through equations 2 and 3 and in table 1. From these calculations, the RN's value ranges from 0.77 to 3.84. This is significantly smaller than the R theoretical value, 24.57, which can be seen to the right of the table and is calculated using equation 4. The relevant values for equation 4 are also listed under R theoretical. This discrepancy can be primarily attributed to differences in the experimental thermal insulation setup, where the top of the load was not covered with insulation as assumed in the theoretical calculation, which allowed heat to escape into the environment. In conclusion, for week 1 results, the vortex tube reduces the load temperature and the heat exchanger and accumulator stabilizes the vortex tube input temperature to be at ambient. The experimental RN's values are different from the theoretical value due to the thermal insulation in the experimental setup. Additionally, more data points are necessary to relate the heat transfer rate and pressure for the heat exchanger and accumulator portion of the system. Finally, next week will involve modeling the cooling of the load in the transient region with the building air and compressor air at 40 and 80 psi. Also, uncertainty analysis will be performed to calculate the uncertainty for the heat transfer rate calculated by the system. Lastly, here are our references.
Thank you, and please let us know if you have any questions about the experimentation we've discussed during this presentation or future experimentation that we plan to do within the following weeks for this lab.